Okay, Chemistry 3101. This is chapter 14, which deals with infrared spectroscopy and mass spectrometry. Today, we're only going to focus on infrared spectroscopy. So that's going to be the only topic of today's lecture. And in order for us to understand how spectroscopy is used and what it's used for, we got to review a little bit of the basics of light and matter. So this goes all the way back to your general chemistry class. In that electromagnetic radiation, which is light, that's all it is. That when we say that fancy electromagnetic radiation means nothing more than light, but we know there's different kinds of light, right? There's visible light, there's infrared light, there's ultraviolet light, etc. Well, we know that light exhibits both wave-like and particle-like properties. You would have learned that in general chemistry. Consequently, electromagnetic radiation can be viewed as a wave or as a particle. And when viewed as a wave, electromagnetic radiation consists of perpendicular oscillating electric and magnetic fields that I have shown here. Now, we need to cover a couple of definitions here, and the first one is a wavelength. And a wavelength describes the distance between adjacent peaks of an oscillating field. So if I just take two peaks at random, and I could take any two peaks, I'll take this peak here. I guess that would be a trough, wouldn't it? But anyhow, if I take these two positions here that are identical and I measure the distance between those, that's called the wavelength of my wave. Okay, so lambda is equal to wavelength, and again, you would have seen the variable wavelength in your general chemistry class. While frequency, so frequency, we use nu, and we call that frequency, and frequency describes the number of wavelengths that pass through a particular point in space per unit time. So wavelengths are measured, they can be measured in meters or centimeters or nanometers or micrometers, it doesn't matter. You need some kind of length, whereas frequency is generally measured in reciprocal seconds, okay, which is the same thing as a hertz. And if you've studied physics, you've probably seen the hertz before. So a reciprocal second and a hertz are identical. Now, accordingly, if we look at the formula between the relationship of frequency and wavelength, we get this. We get that frequency is equal to c divided by lambda. Now, what's c? C is equal to the speed of light, which is 3.0 times 10 to the 8 meters per second, roughly. I know it's not exactly that, but it's close enough. Anyhow, so the relationship that you need to understand is that frequency and wavelength are inversely proportional. Now, what does that mean? That means that when I have a long wavelength of light, I'm going to have a short frequency, or a small frequency. And when I have a short wavelength, I'm going to have a high frequency of light. So you have to understand this formula. You have to understand the inverse relationship between frequency and wavelength. You have to understand that inverse relationship because I'm going to bring it up quite a few times in the class, okay? Now, when we view light as a particle, okay, and this is again harkening back to your days in general chemistry, when we view light as a particle, it consists of packets of energy that we call photons. The energy of each photon is directly proportional to its frequency. And you see the formula here that E is equal to H times nu. And remember that the nu, and I'm just reviewing here already, this is frequency, right? And H, you should remember, is Planck's constant. Planck's, did I spell it correct? There we go. Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, okay? And so we see that if we have the units of our Planck's constant in joules times seconds, and we multiply that by reciprocal seconds, we see that seconds cancel, and we get that energy is given in joules, okay? Now, the next point says here that wavelength is inversely proportional to energy. Now, how would where would I get that relationship? Well, if we go back over here and we look at this formula right here, that frequency is equal to the speed of light over wavelength. I'm going to copy this and I'm going to bring it over to the next slide, and we're going to see how we can prove this statement to be true. Now, if we know that energy is equal to Planck's constant times frequency, and we know that frequency is equal to c over lambda, we can say that energy is equal to h times c over lambda. And there we go. We can see how energy is inversely proportional to wavelength. That's going to be really important for us, okay? It's important for us to understand that when we have a short wavelength, we're going to have higher energy electromagnetic radiation. And when we have a long wavelength, we're going to have lower energy electromagnetic radiation. So here's the electromagnetic spectrum right here. The electromagnetic spectrum is essentially the range of all possible frequencies of light, and it's arbitrarily divided into several regions by their wavelength. Okay, so different regions of the electromagnetic spectrum are used to probe different aspects of molecular structure. We'll talk about that later. But in this chapter, we're going to be concerned with infrared light, right? We're going to be interested in IR, or infrared light. Now you can see that the range of infrared light is not very big. It goes from 2 micrometers to 50 micrometers. And in fact, what the range of infrared light that's actually going to be used in infrared spectroscopy is even narrower than that. It goes from 2.5 micrometers to 25 micrometers. And that's going to be important in a little bit, and I'll show you why that's going to be important. But again, that would be a range inside here, right? You go from 2.5 to 25. And that's the part that's going to be important for us in infrared spectroscopy. All right? Okay, well, let's move on from there. Now, if you're wondering, Mr. Dion, what's the whole point of this chapter? Like, I understand light, I understand frequency, I understand wavelength, I understand Planck's constant, I understand speed of light, no problem. But what's the point? Like, what are we doing this for? Okay? Before we were talking about formulas and functional groups and all these different things. Well, here's the answer. It says when light interacts with molecules, and again, we're interested in infrared light, the effect depends on the wavelength of light used. Again, in this chapter, we're only concerned with infrared light. And the infrared light can be used to probe this, and this is the whole answer right here. We can use infrared light in order to determine functional groups present in a compound, okay? So if you go right back to the beginning of this class, one of the first things I asked you to do is look at functional groups and memorize functional groups and get to know your functional groups. And the reason why is because they're so important in spectroscopy. So again, let me summarize it for you very succinctly. What's the point of the first half of chapter 14? Is that we use infrared light to be able to determine what functional groups are in a compound. So using infrared spectroscopy, you can differentiate between, let's say, a carboxylic acid and an alcohol. You can differentiate between an alkene and an alkyne. You can differentiate between a ketone and an aldehyde, right? So that's the whole point, okay, is being able to elucidate the structure of a molecule. Now, obviously, if you have an unknown molecule and you run an infrared spectrum and you determine that it has a specific functional group, let's say you run an infrared spectrum, you say, okay, it's an amine. I know it's some kind of amine. Well, that doesn't tell you the entire structure of the compound now, does it? No, it just gives you a clue. And so we would use different regions of the electromagnetic spectrum in order to help us to probe different aspects of the molecular structure. So if we want to know about the connectivity of the atoms in a molecule, for that we would use what's called a nuclear magnetic resonance spectroscopy. That's covered in chapter 15. We'll look at that later in this class. And that will give you the actual arrangement of the carbon and hydrogen atoms. It will actually show you the skeleton of the molecule. Okay, so that's pretty cool. So now I've got the skeleton of the molecule and I've got functional groups. We can also use UV vis. We don't cover UV vis in Chemistry 3101, but it can give you some interesting information. And just to add to all of this, now spectrometry is a different subject, a little bit different, but the overall, what's the word I'm looking for? The overall goal of spectrometry is the same. It's that it enables us to elucidate the structure of a molecule. So if you're wondering, what's the second part of the chapter about that we're going to look at in next class, it's about determining the molecular weight of a compound, okay, and some structural information as well. So we'll look at that later on. Anyhow, so let's talk more about how light is going to interact with a molecule. Now, in my day-to-day life, I'm pretty used to classical mechanics, right? Newtonian mechanics. But you've all studied general chemistry. You've all been introduced to quantum mechanics, which doesn't follow the same rules as classical mechanics. And so sometimes it can be a little bit difficult for us to understand, how light interacts with matter. But let me explain it the best way I can. It says here that matter exhibits particle-like properties, but on the macroscopic scale, matter appears to exhibit continuous behavior rather than quantum behavior. So continuous behavior, that would be classical mechanics. So you could write that in here, classical mechanics, that's all the stuff that you would have studied in physics, maybe in high school or something, or in university. Now, in quantum behavior, we know that energy is quantized, okay? So behavior is quantized. So that means it can only have specific values. And again, it goes against, our day-to-day life, what we experience with classical mechanics. Now, here's an example. I'll try to explain it as quickly as I can. It's probably covered in more detail in my video. But let's say you had a tire, spinning on an axle. And I said, I want you to get this tire to spin any speed under the sun, okay? I want you to get that tire to spin at, 60.000002 miles per hour. Can it be done? The answer is yeah, absolutely it can be. It might not be easy, but if you have a device that's sensitive enough, then you would be able to achieve that speed. Now that's classical or continuous behavior. Whereas when we have a molecule, it's not going to exhibit classical continuous behavior. It says matter on the molecular scale, so something that's really small exhibits what's quantum behavior. And instead of spinning, in this class we're going to be talking about vibrations. Okay, it says here a molecule will only rotate or vibrate at certain energies. In this class with infrared spectroscopy, we're going to be concerned with vibrating. Now, if you think about what's a vibration, like the Beach Boys singing about good vibrations. Well, if you were to put your hands on top of a washing machine, it's running or something like that's the vibration. The word is a little different in organic chemistry. The word vibrate in organic chemistry means this movement of bonds. So bonds can stretch and they can bend and things like that, and we call those vibrations. And I'll get into more detail about that in a little bit. But the idea is that the vibration or stretching or movement of bonds in a molecule can't occur at just any frequency, okay, or any energy. It can only occur at specific energy levels. Again, it's not intuitive to us, but that's how it is, okay? At the molecular scale, molecules exhibit quantum behavior. So we have low energy vibrational states, and then we can increase, go up to higher energy vibrational states, okay? And the point is that the horizontal lines in this diagram represent the allowed vibrational energy levels for some, particular bond. And the bond is restricted to these energy levels and cannot vibrate with an energy that is between the allowed levels, okay? And the difference in energy, the delta E, is determined by the nature of the bond, okay? So again, vibration in here where I'm drawing in green is impossible. It's not allowed, okay? It's not going to happen, so I'll just delete it all. Okay, there we go. For the electrons in covalent bonds, vibrational energies are separated by those gaps. Again, we say they're quantized, okay? So only specific energy levels. And here's what's really interesting is now when we subject a molecule to infrared light, it says if the molecule is struck with the exact amount of energy needed, then the light can be absorbed, okay? And then vibrational excitation can occur. So what that means is that the molecule can be irradiated with infrared light, but it can't just absorb any frequency of infrared light. It has to absorb those specific frequencies, right? And if you're saying, why are you saying frequencies and not energy? Well, we know that energy is directly proportional to frequency, right? We looked at that earlier, okay? So infrared light causes molecular vibration. Different types of bonds, again, absorb different infrared energies. And eventually, it gets released from the molecule as heat. And here is a little bit more information about vibrations. Now, the kind of vibrations that, like I told you before, you might think about the vibration of, like, say, a washing machine or a car engine, when it's running, you say, okay, well, that's a vibration. Well, the kind of vibrations that we're concerned about in our class in Chemistry 3101 are stretching, Okay, just like a spring, but you can imagine we have two different atoms. Let's say we had, carbon and an oxygen, right? There can be a stretching of the bond, and you can imagine the bond as being like a spring. Now, obviously, a bond isn't exactly like a spring, but you can imagine it being that way, okay? And then we're also concerned with uh, other kind of bendings, like what are called scissoring and twisting. And if you look at my video that I posted to YouTube, I go into a little more detail about this. Okay, but our class, we're going to mostly focus on stretching, and we're not going to look at things like scissoring and twisting a whole lot. If you take organic chemistry for chemistry majors, you would cover those subjects in more detail. I'm going to skip the part about night vision goggles because I wouldn't ask you anything about that. Okay, but so for each and every bond in a molecule, the energy gap between the vibrational states is very much dependent on the nature of the bond, as I stated a few minutes ago. For example, if you look at the energy gap of a carbon-hydrogen bond, shown here on the left, it's much larger than the energy gap for a carbon-oxygen bond. Okay, they're both of these types of bonds are going to absorb infrared radiation. Okay, but the carbon-hydrogen bond is going to absorb a higher energy photon, right? It's going to absorb higher energy infrared radiation. In fact, each type of bond in a molecule is going to absorb a characteristic frequency that's going to allow us to determine which types of bonds are present in a compound. All we have to do is irradiate the compound, and irradiate just means subject it to infrared light, okay? We irradiate the compound with all the frequencies of infrared radiation, and then here's what's important. We detect which frequencies were absorbed, okay? So, for example, if you have a compound that contains an oxygen-hydrogen bond, let's say, okay, it's going to absorb a frequency of infrared radiation that's characteristic of that oxygen-hydrogen bond. And so that's how we can use infrared spectroscopy to be able to identify the functional groups in a compound. I'm going to skip the part about the whole part about the spectrometer. You can read about that in our textbook, and also about the whole thing about sample preparation. And the reason why I'm going to skip the part about sample preparation, the part about the salt plates, okay, or the KBR pellet or whatever, is because it's not that people don't use those anymore, but they're not used nearly as much as they were a few years ago. Now we have spectrometers that are a little more modern, and the samples are actually easier to prepare, because when I was an undergraduate student, we used to have to prepare the samples on these sodium chloride plates, and it's not easy, okay? So it's actually a good thing that those are a thing of the past. Anyhow, see some of my old scribbles here. Anyhow, so here's what an infrared spectrum looks like. Okay, we have a plot of the percent transmittance as a function of frequency. Now the frequency here, it says wave number. Okay, it's a wave number in centimeters to the minus one. I'm going to talk about that on the next slide, but I want to talk about the percent transmittance or the absorption first. Okay, so we call the plot here, we call it an absorption spectrum, and all of the signals that we see here are called absorption bands. The location of each signal on the spectrum can be specified either by the corresponding wavelength or by corresponding frequency of radiation. But nowadays we use something that's called wave number, which is a frequency related unit, and I'll talk more about that in a second. Okay, so all the scientific community uses wave numbers. Okay, so we have wave numbers and we have percent transmittance. Now, what's about this percent transmittance? If I'm hitting my sample, okay, I have some kind of sample. Let's just say you have your sample of your organic compound. So this is your compound, okay, and you're hitting it with infrared light. Okay, so you're hitting it with infrared light. If most of the light is going to go through the compound, right? The only time light is going to be absorbed is when it matches the energy gap in the specific bonds of the molecule. And so if we look at the percent transmittance, you can see that 100% of the light being transmitted, or most of the light being transmitted, right? If I'm up here, that means that most of the light is being transmitted up here. But the absorption bands, okay, what you see here, here's an absorption, right? Here's one, right? Here's some, you're like, there's some, right? We have all these different absorption bands, those are the frequencies of light that were absorbed, right? So it wasn't transmitted, right? If you have a low transmittance, that means you have a high absorbance. So we had a lot of light absorbed here, we had a lot here, we had some here, so on and so forth, okay? All right, let's talk a little more about the wave number. And you can see that I have some information already put on here with respect to wave numbers and percent transmittance. So going back to this wave number thing, and I'll break it down for you really quickly, okay? The book goes into too much detail, I find, or maybe a little bit more complicated analysis of wave number. It can actually be a lot simpler, okay? Now, I told you that the frequency of infrared light that's used in infrared spectroscopy is going to be from 2.5 micrometers to 25 micrometers. That's the same thing as saying the frequency is anywhere from 2.5 times 10 to the minus 4 centimeters to 25 times 10 to the minus 4 centimeters. Now, if this is a shorter wavelength, right, a shorter wavelength would be higher energy, right? So let's analyze this 2.5 micrometers. Wave number, a faster formula for wave number is that wave number, which is just the nu with this little thing on top of it here, is equal to 1 over the wavelength. Did I put frequency when I meant wavelength? Sorry, my mistake. I should have put wavelength there. So here's our wavelengths of infrared radiation. So if I have 1 over 2.5 times 10 to the minus 4 centimeters, that gives me 4,000 centimeters to the minus 1. Okay, so we can see that our shortest wavelength, the highest energy, gives us a wave number of 4,000 reciprocal centimeters, or centimeters to the minus 1. Okay, if I do the same thing with my longer wavelength, I get that my wave number is going to be equal to 1 over the wavelength, which is 1 over 25 times 10 to the minus 4 centimeters, and that gives me 400 reciprocal centimeters. So the range of wave numbers goes from 4,000 reciprocal centimeters to 400. At 4,000, we're at higher energy or higher frequency. At 400, we're at lower energy or lower frequency. And the whole reason why I'm going over the math here, which isn't covered in its entirety in our textbook, is because I'm going to use the words like high energy, high frequency, right? I'm going to use those words from time to time in this class. All right. Now, if we look at the peaks or the signals or the absorbances in the infrared spectrum, there's 3 important characteristics that we're concerned with in our class. And those characteristics are the wave number. So, for example, where exactly is the absorbance, right? If you look at this absorbance here, if we take the whole thing, if we look at the middle of it here, you'd say it's around, what, maybe around 3,400, right? This is around 3,400 reciprocal centimeters. Or you could, treat it as a range, and we're going to look at that, okay? Let's say, okay, we say it goes from maybe here to here, this whole thing. So you could say it goes from around, what, 31 to maybe 36, right? So you'd say 31 to 3,600 reciprocal centimeters. Anyhow, so the wave number, also the intensity. How big is the peak, right? You can see that these absorbances here are much more intense than these ones up here, okay? So that's intensity. And lastly is the shape. You see how this one here is really broad. It's got a very broad shape. Whereas if you look at something like this, wow, it's really sharp and pointy. Okay, so wave number, intensity, and shape. And we're going to analyze all of those. But first, let's look more at the wave number. We've covered the frequencies of electromagnetic radiation that are used. We've covered where wave number comes from. It's just a convention that all scientists use. We use wave numbers. But let's talk about why different bonds give different signals that come out at different wave numbers, okay? And in order for us to understand that, we have to take a look at this equation right here. So it says the frequency or wave number for a stretching vibration depends on 2 things: bond strength and the mass difference of the atoms that are bonded together, okay? So 2 things: bond strength and the mass of atoms in that bond. All right, so let's take a look at them. Now, you don't have to memorize this entire equation here, which is wave number is equal to 1 over 2 times pi times the speed of light multiplied by the square root of F divided by the reduced mass. Now let's cover what F is, and let's cover what reduced mass is. If you've studied physics, and I'm going to assume that some of the people in this class have studied physics before, you've probably heard of Hooke's law, which is force is equal to K times X, so the spring constant is K multiplied by X, which is the extension. Anyhow, I'm not really concerned about that formula, but this force constant up here is kind of related to Hooke's law, and it is a measure of bond strength. Now, where does bond strength come out in our formula? It's in a numerator, or in the numerator. So we have that wave number. Our wave number is directly proportional to the force constant, or the bond strength. What does that tell us? If it's directly proportional, that tells us that the stronger the bond, right, the bigger the number, the stronger the bond, the higher the wave number. The weaker the bond, the lower the wave number. Okay. What else? We see that wave number is inversely proportional to reduced mass. Now, if you're like, what the heck is a reduced mass? Here's the formula for reduced mass. It would be wise to have this formula in your head, which is another way of me saying you need to memorize this formula. It's just the mass of the two atoms multiplied, divided by their sums. Okay, so the product of the two atoms in the bond divided by the product of the masses of the two atoms in the bond divided by the sum of the masses. The sum of the masses of the two atoms in the bond. Anyhow, the reduced mass. And so since reduced mass is in the denominator, if you calculate reduced mass, what that tells you is that the smaller the atoms are, so the lighter they are, the higher the wave number is going to be. Why? Because wave number is inversely proportional to reduced mass. Now, in my videos, I go into a little more detail with that, and I do some math, calculating some reduced masses. But you can probably just do those in your head. So what's the take-home message from this slide? It says here, the stronger the bond is, the higher the frequency, or the higher the wave number, and the smaller the atoms, the higher the stretching frequency, right? Because this first one is a direct relationship, and this one here is an inverse relationship, okay? Again, you don't have to memorize this formula. You can, you absolutely can, but you have to know that wave number is directly proportional to frequency and that wave number is inversely proportional to reduced mass, and you have to know how to calculate a reduced mass. All right, so if we get into it here, you can see I have some other things scribbled on here. I'll delete those. Okay, so it says the trends in stretching frequency of given bonds can be rationalized based on bond strength and bond mass difference. So we're still talking about the same thing. If we look at the first, number one here, we have carbon-hydrogen bond, a carbon-deuterium bond, carbon-oxygen bond, and a carbon-chlorine bond. So these are all bonds to chlorine, okay? Or sorry, all bonds to carbon. Now, we're going to assume or make an assumption that all of these bond strengths are pretty close. They're all just single bonds to carbon. Now, are they different? Yeah, but not different enough to make a huge difference. Why are there absorbances at such different wave numbers, right? Why are they such big energy differences between their absorbances? And the rationale for point number one is based on the reduced mass, right? The reason the carbon-hydrogen absorbs such a high frequency of electromagnetic radiation is because hydrogen is so light. It only weighs 1. So you would have 12 times 1, which is 12 divided by 12 plus 1. So 12 times 1 is 12 divided by 13, okay? And if you go up to, say, carbon and chlorine, right, and we could even calculate the reduced mass. So I have a calculator here. So if you take 12 and you divide it by 13, you get a reduced mass, which is equal to 0.92 roughly. Let's say if you have carbon and chlorine, then you have 12 times 35 approximately here, divided by 12 plus 35, and that would give you a reduced mass that is much higher. It's 8.9. So as the reduced mass gets higher and higher and higher, since it's in the denominator, right, the wave number, or the energy of the infrared radiation that's absorbed, is going to be lower and lower, okay? Now, if we look at bond strength, it's related to the force constant, so that's summarized in the second point here. All of these bonds are bonds between carbon and nitrogen, but what do we know is that if we go from a single to a double to a triple bond, so we have, right, we have a stronger bond here, and we have a weaker bond here. Okay, weaker bond over here. Well, if force constant or bond strength is in the numerator, that means the stronger the bond, it's going to have a higher absorbance, right? If we have a weaker bond, it's going to have a lower absorbance. All right, so what will we see when we look at a general, infrared spectrum in this class, okay? Well, you can kind of divide the infrared spectra up into a few different places. Here's, just an analysis done by David Klein, and you're going to be expected to memorize some of the absorbances, and I'll go into that in more detail in the next lecture probably. But generally speaking, double bonds, or so we'll start down here on the far right, single bonds are going to have low wave numbers, right? The bonds are weak, okay? We go up to double bonds, they're going to be stronger, so they're going to have higher absorbances. And then we go to triple bonds, which are even stronger, so they have the highest or even higher absorbances. Now, something that might seem like an outlier, but isn't if you understand reduced mass, is that bonds to hydrogen have the highest wave numbers. Now, why would that be? It's not because the bonds are so strong, it's because hydrogen is so light. Hydrogen only weighs 1 gram per mole, only 1 atomic mass unit approximately, okay? So again, you don't have to memorize this formula, but you have to understand the rationale behind it, okay? And if you're thinking, well, I could just memorize all the signals and then I'll be able to get my way through it, you can absolutely do that, but I think that whenever you understand the subject, it's a lot more exciting to study it. All right, so we can split our infrared spectrum into two main regions. Okay, we have what's called a diagnostic region, and we also have what's called a fingerprint region. In Chemistry 3101, you're going to spend probably 90% of your time in, up in the diagnostic region, okay, because it's the simplest region to analyze. Okay, it provides really clear information about double, triple bonds, bonds to hydrogen. Whereas the fingerprint region is what it sounds like. It's anything below 1,500 reciprocal centimeters, and it can be very difficult to analyze, okay? So that's why we don't cover a ton in this class. But if you're wondering, what's the fingerprint region used for if it's so difficult to analyze? Well, let me show you. If you look at these two spectra here, okay, we have 2-butanol, so that's this compound here. We have 2-butanol, and we'll worry about that name later on, and we have 2-propanol. If you draw a line at 1,500, so around here, okay, you draw a line, and you look at the left-hand side of the spectrum, right, the diagnostic part of the spectrum, you see that they look pretty darn close. Okay, they're pretty close, right? You have this broad signal here. You have something that looks pretty similar here. You even have this little blip up here, okay? So it looks pretty similar. Whereas if you just take a quick gander at the fingerprint regions, you can see they're very different. Whoa, very, very different from one another. But again, the fingerprint region can be pretty difficult to analyze, so we won't spend a lot of time in there. A little more information about wave number, and you can see that I've been here already. Anyhow, what about carbon-hydrogen bonds? I want to talk about those in a little more detail here. If you look at the stretching frequencies for all of these carbon-hydrogen bonds, you see that they all give different wave numbers, right? I have 29, 31, and 3,300 reciprocal centimeters. Well, I can answer, or I can provide an explanation as to why they have different absorbances. It's based off of the hybridization of a carbon. So not only is it important for us to understand, okay, if I go back here, I have a carbon-hydrogen bond, let's say, you can also comment on the hybridization of the carbon in that carbon-hydrogen bond. If you go from an sp3 hybridized carbon to an sp2 to an sp, what happens to the bond length, okay, between the carbon and the hydrogen? Well, an sp3 orbital is bigger than an sp2, and an sp2 is bigger than an sp. As the orbitals get smaller and smaller, we go from sp3 to sp2 to sp, the overlap of the orbitals gets closer and closer, right, and stronger and stronger. And so the answer is this, that an sp hybridized carbon-hydrogen bond, okay, is going to be the shortest bond, and therefore it's going to be the strongest of all of these, okay? Whereas an sp3 hybridized carbon-hydrogen bond is going to be the longest and the weakest. And therefore, not only, would you annotate a spectrum and say, okay, I have a carbon-hydrogen bond, you also have to indicate the hybridization of the carbon, because you can tell a difference between the different hybridizations of carbon here, between carbon and hydrogen bonds. All right. Anyhow, so if we take a look at some examples of spectra, and these are just, these come straight out of your textbook. If you look at virtually any, and not everything, but almost every spectrum that we're going to look at in this class, you're always going to have a bunch of signals below 3,000, okay? And those always come from carbon-hydrogen bonds. And why? Because carbon-hydrogen bonds, a single carbon-hydrogen bond from an sp3 hybridized carbon, those are just so ubiquitous in organic chemistry, right? They're in every organic molecule, almost, not every, but almost, right? You have, this is sp3, right? sp3 and sp3. And what did we say? We said they came out around 2,900. You can see that there's a bunch of them here. 2,900 is here, and there's a bunch of different signals, and I'll explain why that is later on, okay? But if you look at an alkane, in an alkane we have no sp2 or sp3 hybrid or sp hybridized carbon-hydrogen bonds, and so we have nothing above 3,000. Whereas in an alkene, okay, we do have an sp2 hybridized carbon-hydrogen bond. And so we see an absorbance at around what? 31, right? This is probably a little lower than 31. Right here it said 31, but remember it said around 31. And so you can see it's a little less than 31, but it's pretty close, okay? And then when we get to the sp hybridized carbon-hydrogen bond in an alkyne, you can see that it comes out around what? 3,300, okay? And again, it says around 3,300. So you have to take all these, and there's always a little bit of wiggle room with these. All right. Now, you got to be careful, though, with alkenes and alkynes. It might be a knee-jerk reaction to say, okay, well, every alkene under the sun, okay, every alkene is going to have some kind of carbon-hydrogen, sp2, stretch at 3,100, and every alkyne is going to have some kind of sp hybridized carbon-hydrogen stretch around 3,300. That's not true. What if you had an alkene that had 4 R groups? Okay, then you have no sp2 hybridized carbon-hydrogen bond. And what if you had an alkyne, that's what we call an internal alkyne, that doesn't have any hydrogens attached to the triple bond? Therefore, you don't have any sp hybridized carbon-hydrogen stretch. So you got to be careful with these kind of things. Okay, and let me just take a break here for a sec. If you're the kind of person that enjoys puzzles, maybe Sudoku or something like that, or crossword puzzles, just any kind of puzzles, you will enjoy spectroscopy, because that's kind of what it is. It's using all the information that you have to solve problems. Well, continuing on in the same vein, let's talk a little bit more about wave number and how resonance affects wave number, or the absorption of a function of light of a specific bond. It says here that if you have a ketone, okay, a ketone, carbonyl, right, has an absorbance at 1720. And again, that's in that neighborhood, but very close to that. But you see here that a conjugated ketone, what's called a conjugated ketone, has an absorbance that's quite a bit lower. It's at 1680. It's lower energy, right? Remember, lower wave number equals lower frequency equals lower energy. Why would it take less energy? Or why would this bond absorb electromagnetic radiation at a lower frequency? It's because it's a weaker bond. Now, why would that be a weaker bond? It's because of resonance. Let me show you how, or let me show you why, okay? If you examine the ketone, okay, and you just look at the ketone, you see that when you draw the resonance structures for the ketone, you get some double bond character here, and you've got some single bond character, okay? It's got a little bit of both, but if you draw the resonance structures for the conjugated ketone, and this is something that we looked at earlier on in this class, is how to draw resonance structures, you can see it's got double bond character, but it's got more single bond character, okay, because of this additional resonance structure. So the answer is this: just because it's got more single bond character, it's going to absorb a lower frequency or a lower energy electromagnetic radiation, and therefore it's going to have a lower stretching frequency. Okay. Now, if you are confused about the word conjugated, Okay? It's something that I mentioned before in class, but conjugated, it just means when you have a pi and a sigma bond alternating. So if you have a pi bond here, then you have a sigma bond, then you have another pi bond, that's called conjugated. So let's say, for example, you looked at the structure of benzene, okay? You'd say that's fully conjugated because it goes pi, sigma, right? And then you have another pi bond. So whenever you have pi bonds that alternate in a molecule, that's called conjugated. So that's all it means, okay? All right. So there we go. And we see the same thing if we look at a conjugated ester, okay? An ester, carbonyl, has an absorption around 1740, but a conjugated ester has a lower absorption, right? Around 1710. Why? Because of the conjugation, it weakens the carbonyl bond, and we know that the bond strength is directly proportional to wave number. So the weaker the bond, therefore the weaker the absorbance. All right, or the weaker the lower the wave number, I should have said. All right, what else? The intensity of the signal. Okay, you see some information that I have written on here about dipole moments. Now, I told you in this class, I'll never ask you to calculate a dipole moment, but I ask you to understand what a dipole moment is. It says here the strength or intensity of infrared signals can vary. We can have a really strong signal, or we can have a really weak signal. And if you're wondering, well, couldn't I have kind of a in the middle of the road signal, like maybe something like this? Absolutely, right? You could say that's a medium signal. Well, why are some signals strong and some signals weak? That is based off of the dipole. Okay, the stronger the dipole in the bond, the stronger the signal is going to be. I mean, that's really just the whole summary right there. Okay, you don't need to know any more information than that. There's a little more information that's provided here, but it says that when a bond undergoes the stretching vibration, it's going to oscillate, right? It stretches back and forth. So the dipole moment is also going to oscillate. And when that dipole moment oscillates, it creates a little electrical field. And the electrical field can kind of act like an antenna, so to speak, for infrared electromagnetic radiation. So the bigger the dipole or the greater the bond polarity, the stronger the infrared signal. That's really the whole summary of this slide and the slide that precedes it. So stronger dipole gives you a stronger signal. So you see a carbonyl has a strong dipole, so therefore it's going to have a stronger signal. And if you have something like this, a carbon-carbon double bond, it's got a very weak dipole, and therefore it's going to have a weaker signal. Oh, right. So here's an example. If you look at a carbonyl, right, it's got a really strong signal. And if you look at an alkene, it's going to have a weaker signal. So again, based off of the dipole. Okay. There you go. Now, if you have an alkene that's completely symmetrical, then it's not going to absorb infrared light at all, okay, because there's no dipole in this molecule, right? This molecule is completely symmetrical, so no dipole, therefore no signal whatsoever. All right, let's move on from there and talk about the shape, because we noticed that some signals were broad and some signals were sharp, and there's a good reason for that too. If we have an alcohol, for example, okay, alcohols exhibit hydrogen bonding. And one effect of hydrogen bonding is to weaken the oxygen-hydrogen bond. Here's a picture depicting hydrogen bonding between two hydroxyls, right? You have one hydroxyl here, you have the other one here, you have the hydrogen bond that's shown here, and the bond gets weakened as a result of that hydrogen bond. Now, if you have a concentrated alcohol, they give rise to broad signals because of this weakening effect. At any given moment in time, the oxygen-hydrogen bond in each molecule is going to be weakened to a different extent. As a result, the oxygen-hydrogen bonds do not have consistent bond strengths, but rather a distribution of bond strengths, and that's why you end up with a broad signal. The shape of oxygen-hydrogen bonding signal is going to be different when the alcohol is diluted in a solvent that cannot form hydrogen bonds, okay? In that case, you're going to end up with a really sharp peak, okay? So this is when we have the oxygen-hydrogen bond participating in hydrogen bonding, and this is when we have the oxygen-hydrogen bond not participating in hydrogen bonding. Okay, so when you're in a solvent that can't hydrogen bond, it's likely that the oxygen-hydrogen bonds are not going to participate in the hydrogen bonding interaction, and again, we get that narrow signal. Then what we see here on this spectrum is that when the solution is neither concentrated or dilute, you end up with both signals. You get two signals, okay? The molecules that are not participating in hydrogen bonding give you the narrow signal that says free hydroxyl next to it. And the ones that are participating in hydrogen bonding give you the broad signal, okay? All right. Anyhow, when oxygen-hydrogen bonds participate in hydrogen bonding, they generally produce a broad signal between 32 to 3600 reciprocal centimeters that you can see here. All right. Anyhow, so let's move on from there. Now, if we have a carboxylic acid, this is probably the easiest functional group of all to recognize. It says the carboxylic acids exhibit a similar behavior, only more pronounced. If we look at this spectrum here, so this is a spectrum of butyric acid. So butyric acid is this. That's butyric acid. You notice the very broad signal on the left side of the spectrum. It stretches all the way from around, all the way from around 2200 reciprocal centimeters, all the way up to around, I don't know, what is this, 3600 reciprocal centimeters, maybe. So it's really broad. And the reason why the carboxylic acid has such a broad range of oxygen-hydrogen stretching is because they can form these hydrogen bonding dimers that are shown here. And so it can vary the strength of the oxygen-hydrogen bond greatly. And so that's why we end up with such a large range for the oxygen-hydrogen bond in a carboxylic acid. And notice that you get the carbonyl as well in a carboxylic acid, right? That comes out around 1700. Okay. We got one more section on shape, which deals with amines, and then we're going to talk about some analysis of some spectra, and then we'll get into some examples. I know there's a lot of kind of background at the beginning here, but I promise we'll get to look at some examples before we finish lecture today. So it says here that you can have a primary or a secondary amine that can exhibit nitrogen-hydrogen stretching signals. Now, what do we know about nitrogen-hydrogen bonds? We know that they're capable of hydrogen bonding, right? We know that the requirements for hydrogen bonding are either a bond between hydrogen and oxygen, hydrogen and nitrogen, or hydrogen and fluorine. Well, a primary amine is when you have a nitrogen with two hydrogens attached to it, and a secondary amine is when you have a nitrogen with only one hydrogen attached to it, okay? Now, primary amines exhibit two signals for the nitrogen-hydrogen bonds, okay, which are going to be broad, right, because of the hydrogen bonding. And you might think, it might be a knee-jerk reaction to say, well, I've got two bonds in a primary amine, so two bonds, two stretches. That's not true. That's not the reason why. It's actually because the nitrogen-hydrogen bonds, the two of them can vibrate in two different ways. You can have symmetric or asymmetric stretching. Now, hopefully this will work. But this is a page from Wikipedia, and the two types of stretching for an amine are what are shown right here. The two bonds can stretch together at the same time, symmetric stretching, or they can kind of alternate here, like back and forth and back and forth. That's called antisymmetric or asymmetric stretching. So these are the two types of stretching that we see for a primary amine, and that's why a primary amine gives us two signals. Go back to my thing here. But a secondary amine only has one type of nitrogen-hydrogen bond, and therefore it only gives you one signal. All right, so here's how you would distinguish between a primary and a secondary amine. You look at the primary amine, you have two stretches. They're not as strong as oxygen-hydrogen bonds. Why? Because the dipole isn't as strong, but you have two absorbances around. It's hard to read it off here. I don't want to. Yeah, so maybe around 3350 and 3450, something like that, because my line isn't perfectly straight. And then for a primary amine, you have one absorbance, okay, a single absorbance, and in this case, it's around what? It's around 3,300 reciprocal centimeters. So again, that's how we would differentiate between a primary and a secondary amine. All right. So table 14.2 in the textbook, it would be wise for you to memorize that table. And again, I'll give you more information about that during the next lecture. You don't have to have it memorized for today, but it shows you all the important signals in infrared spectroscopy for this course. It's not an exhaustive list of important signals, but it gives you all the ones that are important for our class. So what are you going to do when you're analyzing a spectrum, right? Imagine you're on the next quiz a week from today, and you're looking at an infrared spectrum. How do you analyze it? Well, the first thing you're going to do is you're going to look in the diagnostic region. You're not going to spend a whole lot of time in the fingerprint region. You're going to go to the region between 1600 and 1850, and you're going to look for double bonds. Maybe a carbon-carbon double bond, maybe a carbon-oxygen double bond, maybe a carbon-nitrogen double bond. We won't really look at a whole lot of carbon-nitrogen double bonds, but it's possible. Then you're going to go up to a higher wave number, 2100 to 2300. You're going to look for triple bonds, either a triple bond between two carbons or a triple bond between a carbon and a nitrogen. So those are some possibilities. And then after that, you're going to look for bonds to hydrogen, right? Things like nitrogen-hydrogen bonds, oxygen-hydrogen bonds, carbon-hydrogen bonds, and you're going to look at the hybridization of the carbon in the bond, right? If I help you with the double bond, so it could be a carbon-carbon double bond or a carbon-oxygen. All right, there you go. Then you're going to analyze the wave number, the intensity, and the shape for each signal, and you'll be able to get some information, okay? Then when you look at the region where the bonds to hydrogen are, and this is just a David Klein thing. He says you can draw a line at 3000 and focus on the signals above it, right? Because we know that, and we've looked at this already today, that when we have an sp2 carbon-hydrogen bond, the absorbance is going to be around 3,100 reciprocal centimeters. If we have an sp hybridized carbon-hydrogen bond, it's going to be around 3,300 reciprocal centimeters, give or take a little bit. If we have a primary amine, you can see that that's coming out maybe around, I don't know, 3,350 reciprocal centimeters, okay? And then if we have our oxygen-hydrogen bond, that's in a range of 32 to 3,600 reciprocal centimeters, because those are almost always going to be broad in this class. All right. So one of the most powerful, or one of the best reasons to use infrared spectroscopy is to be able to differentiate between two compounds. Okay, let's say you're doing a reaction, and we haven't really even looked at any reactions yet in this class. Let's say you're doing a reaction where you want to convert one functional group into another. You can use infrared spectroscopy to determine whether the reaction has worked or not. If you were trying to do this reaction that's shown right here in the lab, the problem with doing this reaction, I mean, there's no real problem, but one of the difficulties is one of the preferred methods by organic chemists to monitor reactions is to either use TLC, which all of you have tried probably at least one point in your life using thin layer chromatography, or to use what's called gas chromatography, mass spectrometry, okay? The problem with these molecules, both of this alcohol and this ketone, is that neither of these will show up on a TLC plate because they don't have a chromophore, okay? They don't absorb UV light. And in terms of gas chromatography, they would also not absorb, they wouldn't give you any kind of absorbance, so you wouldn't be able to see them. But if you were to monitor your reaction by infrared spectroscopy, right, you could clearly see that you have a hydroxyl here, right? And we know that the oxygen-hydrogen bond has a stretch of around 3,200 to 3,600 reciprocal centimeters. Now, if the reaction works, we know that we have a carbonyl. And a carbonyl, let's just say, since it's a ketone, plug this back in. Since it's a ketone, we'll say it's around, 1725. Okay, let's say this is around 1725 reciprocal centimeters. So you can monitor the reaction by the disappearance of this signal and the appearance of this signal. So that's a way to monitor a reaction like that. All right, well, we're not going to start mass spectrometry today. I promised we wouldn't do that. And so what we're going to do right now is we're going to look at some problems, and we're going to look at some problems that come directly from our textbook, okay? Now, again, in order for you to solve these problems, you need to have table 14.2, or if you go on our classes, if you go on our Canvas page, and I'm looking at chapter 14 right now, you'll see third file down, it says IR-NMR tables Klein, okay? And I can post that in a chat right now. Just give me 1 second. And I will give you that table for your quiz. Okay, so that you're going to be able to bring that table into your quiz. Where is it? Here it is, right here. Just give me 1 second, and I'll post it in the chat in case you don't have your Canvas open or something. Okay. There we go. So, just give me a second. It's uploading it. There we go. Okay, so I have the table posted in the chat. And let me double check here. Don't have the table here. Okay. I don't have the table on my iPad, but if you download that table, you'll see at the top it says IR absorption frequencies of specific functional groups. Again, I just posted it in the chat, and it's also in Canvas. It says IR-NMR tables Klein. Can everybody see that table? Or anyhow, maybe I shouldn't ask that.
Yes.
Okay, good. Okay. So the important thing is that you understand is that I will give you that table for your first quiz, okay, or for your next quiz. You're going to have that with you. You see the part below, the infrared signals? It says typical values for NMR shifts or whatever. You don't have to worry about that at all, okay? That's not even going to be used for the next quiz. So since Dr. Anderson and I both teach this course, he teaches on sequence and I teach off sequence, right? We have a lot of gentlemen's agreements about what we give our students, you know, so that it's fair, or whoever your instructor is. So if you are in Dr. Anderson's class, he'll give you this table. And if you're in my class, I'll give you this table. Now, here's my disclaimer about the table. There's nothing wrong with using the table, okay? Everybody has to look up a signal once in a while, you know, you're like, I'm not 100% sure. But I would if I was you, I would try to treat it like training wheels. You know, you're going to use it a lot at the beginning, but the more familiar that you become with infrared spectroscopy, the less and less you'll have to use it. Okay. I'm not saying I'm not going to give it to you, but I would try to get used to using it with trying to analyze without. Just give me a second here. All right. Sorry about that. Teaching during coronavirus. All right. Can everybody see my slide that says Chem 3101 IR practice Klein?
Yes.
All right. Okay. So if you were like, Mr. Dion, I didn't follow you 100% on what you were talking about signals and stretching and all this. Well, it's important that you understand that. Okay. So if you didn't follow me 100% for whatever reason, be sure to go back, look at the book, look at the videos that I posted to YouTube that are in my announcement. There's a whole playlist on there. But I can tell you right now, the best way to get the concepts in infrared spectroscopy to crystallize in your mind are to practice. Okay. Now you knew that was coming, right? Didn't you? Okay. You've heard me. I've been teaching, you know, you've been taking organic chemistry long enough to know what Mr. Dion's going to say. It's going to be practice, practice, practice. So I'm going to give you a second to look at the table that, again, the one I posted in the chat. I'd use that one instead of the one in the book because that's the one you're going to be given on your quiz, and it's got all the information that you need. And I'd like you to look at these there's 1, 2, 3, 4, 5, 6 spectra. I can only put 4 on here at a time. And all you have to do is answer, is this, are each of these spectra, is it an alcohol, a carboxylic acid, or is it neither? Okay, I'm going to give you a second to look at them. And I'm just going to grab a drink of water, and then I'm going to tackle these with you. I have to find my water first. Okay.
Too bad for me.
Okay. So if we look at the table, okay, excuse me, it says that an alcohol gives you a broad oxygen hydrogen stretch from 3650 to around 3200 reciprocal centimeters, right? Alcohol 3650 to 3200 reciprocal centimeters, and it's going to be broad. Okay, and again, that's around there. Doesn't mean it's going to be exactly, right on those numbers. And if you look at the table, it says that a carboxylic acid is going to give you an oxygen hydrogen stretch. I want to make sure I get it exactly the way that it is on the table. It says it's around from 3,300, okay, to 2,400 reciprocal centimeters, and it says it's broad as well, okay? Now, there is other information provided for the carboxylic acid, like the carbonyl, which is at 1710, so you get the carbonyl at 1710, okay? And it also gives you information about carbon-oxygen stretching for both of them. Well, let's just start with that, and let's look at A. I want to know if any of my students have an idea, and I'm sure you all do. Who's got an idea about A? Would that be a carboxylic acid, an alcohol, or neither? Or neither? Yeah, absolutely. I see two students fired off answers really quickly. They both said, Mr. Dion, that's an alcohol, right? This is an oxygen, hydrogen stretch, okay, from an alcohol. Alcohol. All right, how do I know that? It starts here around, look, this is 3,000, this is 3,100, this is 3,200. I need a new prescription. Let me stretch this out. Like, there we go. Okay, so it kind of starts around 3,200, right? And it goes to around 3,600, right? And it's broad, okay? So the way I would annotate that is, I'll do it a little neater. I'll say like this. I would say alcohol, OH, stretch. That's how you would label that. Now, also, if you look by alcohol, it says you have carbon-oxygen stretching in the fingerprint region from 1250 to 1,000. So here's 1,000, and here's 1250, would be around here. Now, the only thing that comes out around 1250 or in that range is this signal here. So I would circle that, and I would say carbon-oxygen stretch. Okay, and then if you're like, well, Mr. Dion, there's like 2 peaks here. Yeah, I'd circle the whole thing like that, and I'd say that's probably a carbon-oxygen stretch. Let's go to B. Anybody have a feeling about B? Is it a carboxylic acid, an alcohol, or neither? And I know you guys all have feelings about this. Anybody have a feeling about B? Yeah, thanks, Byron. The answer is definitely neither, right, Skylar? Right, Jessica, you're all correct, okay? Look, if you draw a line at 3,000, okay, and Mr. Dion's not the best at drawing these kind of straight lines, but you can see, okay, there's no oxygen hydrogen stretching up here. Therefore, the answer is neither of those. Okay? There's nothing up there. Whoa, whoa, whoa. Let's look at this one. Who's got a feeling about C? Yeah, I knew you'd have some strong feelings about C. Absolutely. You're 100% correct. This is definitely a carboxylic acid, isn't it? Carboxylic acid, easiest functional group to recognize in infrared spectroscopy because it takes up the whole damn thing, right? It takes up 1/3 or, the entire spectrum. Okay, so I would say oxygen, hydrogen, stretch, carboxylic acid, right? Because it goes in that range from around 2,400. So where's 2,400? Around here Right? It goes all the way from here up to around 3,300. So you got 3,300 around here. Like it's even farther than that. But again, you have to take those numbers with a grain of salt. Okay, might not be exactly that. Is there anything else in this spectrum that would tell you that this is a carboxylic acid or any other part of the functional group? Anybody? Yeah, absolutely. Courtney, Jonathan, you're both 100% correct. And the way you would do that is you would put carbon, oxygen. Where's my pen? Say C double bond O, so a carbonyl stretch like that. It also says that you can have carbon oxygen stretching between 1320 and 1210. So that would be, oh jeepers, that would be around here. So 1320. So maybe this, you might want to circle that and say CO stretch. Anyhow, let's answer the rest of them really quickly. What about D? Is that a carboxylic acid, alcohol, or neither? D. Yeah, thanks, Courtney. The answer is neither. If you go above 3,000, right? No oxygen, hydrogen stretch. Okay, therefore, neither. Let's go to E. What about E? Who's got a feeling about E? Oh, right. Somebody says an alcohol. Somebody else says an alcohol. Absolutely. So I'd say here oxygen, hydrogen stretch. Okay. Alcohol. Right. I'd say probably, where's the carbon oxygen? This is 1,000 to 1,250. So this would probably be the carbon oxygen stretch. Around there. And then the last one, come on, everybody knows what this is. This is the oxygen hydrogen stretch from a carboxylic acid. Okay, and here's the CO stretch from the carboxylic acid, right? And then, again, I can't see very well here, but this might be the carbon oxygen stretch. We'll leave it out for this one, but you can definitely differentiate between those. Okay, now I'm not ending class early because I don't do that. But I want to show you or explain a couple things to you quickly, and I can post an announcement about this if you want. But if you go into Canvas, so I'm looking at Canvas right now. I don't have it hauled up on my screen, obviously. But if you go into Canvas and you look at the module for Chapter 14, you notice that I have a little more files in there than normal, right? I have all kinds of stuff in there, okay? I have the IR NMR tables, then I have the IR practice Klein, then I have the next file says Chapter 14 IR practice, and then it says V3 next to it. If you click on that, it opens up a whole holy host of 9 problems. Okay, can everybody see that? The 9 problems there? Okay, it's called Chem 3101, Chapter 14, IR Practice V3. Yeah, okay, good. Thanks, Jessica. Okay, so that, those problems, and there's 9 of them in there, okay? Those are going to be very close to the problems that you're going to have on your quiz that deal with IR, being able to look at a spectrum and determine what compound. I have on my YouTube channel, okay? If you go in my YouTube channel, the infrared spectroscopy playlist, and you go down to infrared spectroscopy practice 1 and then 3 and then 4, 5, 6. I don't know why I skipped 2. But anyhow, the guided solutions for all of those problems are on my YouTube channel, okay? So what I'll do is I'll post an announcement about that because I'd like you to try to work through all of those problems before class on Wednesday. And if you're thinking 9 problems, oh, Mr. Dion, this can take me, trust me, it will only take you 25 minutes to do it. It's not long. The problems look big because you're looking at a whole spectrum, okay? Does everybody give me a thumbs up if you're like, yes, I think I can get that done before next class? Anybody? All right, thanks, Moira. I'll take it. So this class is, always a tough one for me because, I want to talk about the theory. I enjoy the theory of infrared spectroscopy, but I know that as your instructor, I've taught the class long enough to know that I really got to get down into solving some problems with you. So what we're going to do next class is we're going to spend the first half an hour looking at other problems of IR. We'll find some more problems, or maybe we'll look through the problems that I even have the guided solutions for. Quickly, we could do that. We'll look through the rest of these problems. I have some other problems here. Make sure to take a look at 1410 and 1412, okay? So let me go back to my screen or my camera. Stopped broadcasting. I want to give you a couple more announcements. Okay, where am I? Okay, so look, in order for you to master infrared spectroscopy and mass spectrometry, we've got to spend time, concentrating on problem solving. And so, on Wednesday, we're going to spend a lot of time looking at IR problems. I'll lecture on mass spec because I have to, and then we'll look at some problems that deal with mass spec as well. And then hopefully on Friday, we'll spend even more time practicing. And if you are in the lab, I don't like to marry the two classes a whole hell of a lot because they are separate classes and some people are enrolled in one and not in the other. But this is just a disclaimer for anybody who's hearing my voice who's in the lab, which I know is most of you, okay? If you're in Chem 3102 and you look at the lab lecture, it says that 1 week we're going to talk about IR and MS, so infrared and mass spec. That week, I'm not going to go over any theory at all because all of you will have either taken it with me in this class or anybody, and I'm preaching to people who wouldn't be in this class. But if somebody's enrolled in this class, in that class, and isn't in this class, that means they've already taken organic chemistry, right? So they would have already heard the background. And so when we get into it in the lab, we're going to spend a lot of time just problem solving, okay? So yeah, that's basically the crux of it. Okay, so again, on Wednesday, the first thing we'll do is look at more problems, and then on Friday we'll try to look at even more problems, and of course on Wednesday I have to talk about mass spec. All right. Anyhow, there we go. So I'll post